My name is Erik Sü, and I'm presenting to you the paper Enhanced Performance and Privacy for TLS over TCP Fast Open. Co-authors of this paper are Tobias Müller, Christian Burkhardt, Hannes Federath, and Matthias Fischer. All of us are from the University of Hamburg. Transport protocols are important to protect the user's privacy. Transport protocols such as TCP Fast Open should not allow distinguishing Alice and Bob as the sender of a message. The quality of experience for web users increases significantly if they don't have to wait for websites to load. The TCP Fast Open protocol aims to optimize the performance of the TCP protocol by reducing the delay of the connection establishment during reconnections to the same server. The question arises whether we can further optimize the performance of the TCP Fast Open protocol. The Fast Open extension of the TCP protocol has been standardized as Request for Commons 7413 in the December of 2014. By now, the TCP Fast Open protocol is supported within various kernels of popular operating systems such as Windows, Mac OS, or Linux. The TCP Fast Open protocol has two handshake modes, the initial handshake and the abbreviated handshake. During the initial handshake, the client starts by sending a SYN package along with a Fast Open cookie request. The server then responds with a SYN-ACK and attaches a Fast Open cookie to this message. Finally, the client sends an ACK and starts sending application data. The Fast Open cookie received from the server is cached within the TCP cache, and the client will reuse this cached Fast Open cookie if during a future connection attempt the client and the server IP address matches the one of the previous TCP Fast Open connection. Then, during the abbreviated handshake, the client starts by sending a SYN along with the Fast Open cookie it retrieved from the cache and sends application data. The server responds with a SYN-ACK and the client finally sends an ACK. In total, this saves one round trip time compared to the initial handshake. Reusing a cached Fast Open cookie across different connections can allow the server to identify the client device across these connections. TCP Fast Open has the requirement for the client to have a matching client and server IP address when the Fast Open cookie shall be reused. This makes it especially interesting to compare tracking via IP addresses to tracking via Fast Open cookies. One key difference between these tracking mechanisms is that Fast Open cookies allow to distinguish devices behind a shared IP address. This is obviously not possible for tracking via IP addresses, and it is quite popular to have shared IP addresses, especially in the IPv4 address space. So we assume that the server is issuing unique fast open cookies independent of the client's IP address, and then it will be able to distinguish these devices based on the fast open cookie that they show during the reconnection attempt. Another key difference is when we assume network address translators that have a dynamically changing public IP address. In this scenario, the change of the public IP address of a NAT gateway limits the trackability or the tracking period via the IP address mechanism. However, the client device and the private network of the NAT device has a static IP address. And thus it observes for itself that it has a matching client IP address and a matching server IP address, which is the server within the public IP address space. And thus, to reuse the fast open cookie, it will fulfill that requirement of these matching IP addresses independently of the publicly visible IP address assigned to this NAT. To evaluate the identified tracking mechanism, we conducted browser measurements. We found that fast open cookies represent a tracking mechanism which is based in the kernel of the operating system. And thus it is quite difficult to handle for modern browsers. We found that the tracking periods are basically unrestricted as long as the TCP fast open cache is not emptied by, for example, rebooting the operating system. For popular browsers such as Firefox, Chrome, Edge, and Opera, we found that tracking is feasible across the private browsing mode or browser restarts. Furthermore, we found that even tracking across different applications on the same device is feasible using this tracking mechanism. For example, cross-browser tracking is possible using fast open cookies. We reported our findings to various browser vendors, and Mozilla reacted by stopping the TCP fast open protocol within its Firefox products, and Microsoft stopped using the TCP fast open protocol within the private browsing mode of Microsoft Edge. TCP fast open requires a matching server IP address to conduct abbreviated handshakes. This can be a performance limitation. We studied this performance limitation by connecting 10 consecutive times to the 30,000 host names of the Alexa top million websites that support the TCP fast open protocol. We find that during the second connection to these host names, on average, 40% of these connections fail to conduct an abbreviated handshake. During the third connection to these host names, we find that still 25% of these connections fail to conduct an abbreviated handshake. In total, we we find that real-world load balancing is not well anticipated by the requirement of matching server IP addresses. To overcome the introduced privacy and performance limitations, we propose in our paper the TCP Fast Open Privacy Protocol. This protocol presents a cross-layer approach between TCP and TLS. The proposed TCP Fast Open Privacy Protocol has two handshake modes, the initial handshake and the abbreviated handshake. The client starts the initial handshake by sending a SYN plus a TCP Fast Open cookie request. The server responds with a SYN ACK and forwards the cookie request to the TLS application layer. Later on, the client acknowledges with an ACK message and sends the client hello of the TLS protocol. The server responds with the server hello of the TLS protocol, and to support TLS session resumption, it issues a new pre-shared key, which contains the TCP Fast Open cookie. The client caches the received pre-shared key, including the TCP Fast Open cookie, and associates it with the server's host name. Later on, when the client wants to reconnect to the same host name, it first validates that the cached pre-shared key and TCP Fast Open cookie have not expired in the meantime, and then it sends the SYN plus the TCP Fast Open cookie message, as well as a client hello of the TLS protocol and the encrypted request. The server validates this information and then accepts the TLS data. It responds with a SYN ACK over the SYN message and the TLS data, and as well sends a server hello message of the TLS protocol and a response, an encrypted response. In total, this abbreviated handshake can save up to one round-trip time for the TCP connection establishment and one round-trip time for the TLS connection establishment. We observe that the fast open cookie can only be observed by a network observer a single time during the first message of the abbreviated handshake, because during the initial handshake the TCP Fast Open cookie is issued over an encrypted connection. The TCP Fast Open Privacy Protocol addresses all identified privacy issues of TCP Fast Open. For example, the privacy problem that TCP Fast Open is a clear text protocol and a network-based attacker can read all exchanged messages and conduct tracking based on these messages is prevented by TCP Fast Open by using single-use cookies and an encrypted channel to issue the TCP Fast Open cookies. Thus, a network-based attacker can only read a single time single-use cookies during the connection establishment of the abbreviated handshake. Tracking across private browsing modes is a problem of TCP fast open that can be addressed by TCP fast open privacy if a context identifier is used within the TLS cache. Thus, the context of the private browsing mode or the normal browsing mode is associated with the cached TCP fast open cookie. Tracking across browser restarts is addressed by either using such a context identifier as well, or I assume that the browser will clear the TLS cache anyway during the browser restart and thus also destroy the cached TCP fast open cookies. Tracking across user applications can be possible if multiple user applications use the same TLS cache. And in that scenario, one could use a context identifier for each application and thus prevent that an application is reusing TCP fast open cookies of another application. And the tracking periods in TCP fast open are basically unrestricted. And for TCP fast open privacy, one can use expiration times for the cache cookies and then reuse only cookies with a valid expiration time for the connection establishment. To evaluate the performance of the proposed TCP fast open privacy protocol, we implemented a prototype of this protocol and compared it with respect to the computational overhead to the TCP fast open protocol. In total, we found only insignificant differences between TCP fast open over TLS and TCP fast open privacy over TLS for this evaluation. Furthermore, we conducted a simulation which considered the studied load balancing of the Alexa top million websites that support TCP fast open. Here we found that there exists a significant performance advantage of associating the cached TCP fast open cookies to the host name of the respective online service compared to the TCP fast open approach of associating the TCP fast open cookie to the server's IP address. In the simulation, we found that for the first revisit of a website, which requires 20 connections to different host names, we find a probability of 39% that no round-trip time is saved for the TCP fast open protocol over TLS, and a probability of 61% that a single round-trip time is saved for the TCP fast open protocol over TLS. For the proposed TCP fast open privacy protocol over TLS, we always find that it allows for this scenario to save 2 round-trip times, which in total is a significant performance advantage of our proposal. To conclude, our paper indicates a lot of limitations of TCP fast open privacy. First of all, it is a kernel-based tracking mechanism, and it allows network observers to track users. It allows for unrestricted tracking periods. It enables tracking across private browsing modes, browser restarts, and different applications. And it has a significant failure rate if it is used under real-world circumstances. Furthermore, we found that browser vendors such as Mozilla and Microsoft reacted to our findings and stopped TCP fast open, at least in parts of the browsers. And we proposed a new protocol, the TCP fast open privacy protocol, which addresses the privacy and performance limitations of TFO. Thank you for listening to my presentation.